It's okay. I'll get some batteries.
Good morning, everybody. Can you all hear me? Yeah. Okay, good. All right. So, as part of this refresher course on statistical physics, we thought we'd also have a set of lectures on stochastic processes, I think it's called. See, process, the word you'll all know. Something has happened, some process. What is the meaning of stochastic? Stochastic sounds a little forbidding, but it's a very simple idea. That something may happen, but it may not. Chance, probability, that's what enters. Now, stochastic processes, what I'm going to talk about really is dynamics. Dynamics, you're all familiar with. The idea of dynamics means time development, how a system develops in time. Classical mechanics, we know, we've just heard Professor Mukunda describe how systems of particles, n particles with coordinates, etc., how they evolve in time. And there are, very important and beautiful laws, first enunciated together by Newton, which tell us how the system evolves. Come to quantum mechanics, also very beautiful set of principles which tell us how a quantum system will evolve. And you're familiar with the idea of a wave function, etc., in quantum mechanics. So these are the two well-known types of dynamics that you'll often encounter as students or teachers or whatever. But there's a third type, and that is the one I'll talk about. And that is, what I'm calling stochastic dynamics, where things happen with an element of chance. The systems we are typically thinking about in these lectures are classical systems. It's not that they don't obey Newton's laws, they do ultimately. But in the description that we are giving, it's a little coarse description. Sometimes you can, get away and successfully do this. You ascribe an element of chance to what may happen in a system, of course with some physical motivation at the back of your mind. The familiar system is, of course, a particle, maybe micron-sized particle like a colloidal particle, which is in a liquid, beaker of water, and it's buffeted very frequently by water molecules. So it gets impacts from all sides all the time. Of course, in principle, deterministic, described by Newton's laws, but in practice, there's so many things happening that you might regard this process as probabilistic. There's a certain probability of being hit from this side, from that side, etc. And then you describe the motion itself in terms of probability. So this is the sort of motion that I will ultimately be heading to. Now, in this endeavor, there's a simple and very easy to imagine model that plays a very central role in the whole theory. And that is the model of a random walk. I wanted to know, has anybody heard of the word random walk earlier? Yes, I see a lot of nodding. Okay, so I presume you have. Even if you haven't, I'll define it in a minute by doing a random walk myself. Okay, yeah. So sometimes going left, of course I've moved more left than right. My left, your right. But sometimes right. And actually nobody knows, not even I, what I'll do in the very next instant, whether I'll go left or right. There's a certain probability of going left, certain probability of going right. Simplest situation will be probabilities are equal. If they're equal, what will the values be? Half and half. Why? Because it has to add up to 1. You already have an intuitive understanding of probability. So what is probability? Probability, you can think of in many ways, but we will think of, outcomes of a possible experiment or outcomes of a possible thing that could happen, and there are many possible outcomes. You don't know which one will happen, and then you might assign a probability to each. What will it mean? It would mean that if you were to do an experiment or do this thing that we are talking about many times, so there are lots of trials. Each one is called a trial. So if there are outcomes, and there are n trials, let's say, and we have n1 times that we. Is that me? Better? Yeah. N1 of these, N2 of these. These are, you'll call these as successes. N1 times you succeed in reaching state 1, 2, 3, 4. And the ratio of N1 divided by N, when N becomes very large, you expect will go to a certain ratio. That is the probability. So that is the intuitive notion we'll use. The probability is like, you repeat this many times, and you have a number of trials, a number of successes, and the ratio will give you a probability. Does that make sense generally? We're using an everyday version of probability. So before I start, let me also tell you, there are 2 or 3 references to the lectures that I'll give. One is a very beautiful and very influential article by Chandrasekhar. You'll all know Chandrasekhar. You all probably know of him in the context of astronomy and astrophysics. The Chandrasekhar limit, black holes also later, and many other stellar clusters, but also Chandrasekhar of stochastic processes. So he wrote an article in 1943 called Stochastic Processes in Physics and Astronomy, and it's still, in my opinion, the best introduction to the field. So to all students, I would say, students, teachers, or whoever is new to the subject, read this. It's readily available in reviews of modern physics, and here's the reference. It's also one of the papers published in a compilation of papers edited by Nelson Wax. Which has a number of other papers also, but Chandrasekhar's is the first, and you must read this. He addresses a wide variety of problems because probability and these notions apply to a wide variety of stuff. Whether you're talking about particles sedimenting in a beaker, or you're talking about stars and stellar clusters, you'll find all these covered to some extent in this article, and you'll see the wide range of applications. This is a book that has been handed out. It's a readable book, and it's a very good introduction. It's a sort of a sprightly, book. And if you actually read it and try to understand everything, you'll understand a lot. I would urge you to do this, to have a look at this book. There's a third book which also I will recommend, and that is by Van Kampen. It's called Stochastic Processes in Physics and Chemistry. So these 2 books are part of the collection that has been set aside in the library, and you can consult them if you like. All right. So now let's begin by discussing the random walk. Okay. So as I said, the simplest version of the problem is my notes is that I have a walker, and let me just think about a person doing a walk on a one-dimensional lattice. So here's the origin. Etc. So there's a line from -infinity to infinity. There are points 1, 2, 3 on the right and on the left, and the walker, let's say, starts at the origin at a certain instant, and we will think of the allowed moves being one step right or one step left, wherever the walker is. All right. What we'll ask is, after n steps, so the first question to ask is, where will the walker be? Okay, let's ask this question. So we can say location m. M is an integer, given all this. The largest value m can have is n, because at most the walker would have moved n steps, right? Now, the first thing that you do when you have a problem in probabilities, first of all, think of all the options. Options meaning what could have happened. There are n steps. Okay, so in your mind you write down, maybe the first step was right, second step was right, third step was left. This was one sequence of, possible walk. But then other walks you can construct very easily by changing something or the other. Here's an equally valid walk. Here's another, etc. And you can keep writing these. Can anyone tell me how many options there are? How many ones? Sorry? Louder? Sorry? 2 to the power n. That is actually correct. Yeah. Why? Simply because at every step there are 2 options, right or left, and the next step, I've assumed, is independent of what happened earlier. Anyway, the number of options is 2 at each step, and so you multiply each, because given this there are 2 more and 2 more, so it's 2 to the n. Is that all right? Now, if you were to ascribe a probability to each option, it makes sense, given what I've said, that the probability of every option will be equal. In other words, the chance that I've made only leftward steps for 7 steps is the same as any other, which is right. And therefore, the probability of any one of them is 1 divided by the total number, which is 2 to the n. Okay. By the way, I should say that even these notions are not very, very obvious to people. You can easily transcribe in your mind this to heads and tails. Heads will be right, tails will be left, so there's a sequence of heads and tails, which is why I should say historically the whole development of probability started from the theory of gambling. This is De Moivre, and they were talking about games of chance. And gambling and probability have a lot to do with each other. If you read Feller's book, the most instructive chapter in that book is called The Gambler's Ruin. Please read that. So when you go to a casino, you should know what to do. We'll illustrate some of these things as we go on. Okay, but fine. Yeah, I forget where I was, but let's pick up again. All right, so now let us ask then, we're talking about this location m, but m itself is what I'll call a random variable, in the sense that we're not sure what m is. It depends on the sequence of things that happened, and if we repeat the experiment again and again, we'll get different values of m, right? So let's ask what is the probability that after n steps I will land up at point m. So let me call that P of m and n. I don't know how to get rid of this. My mobile or something is doing it. It actually showed low cell. Change the cell, the battery. Volunteers, can you do something about this? I mean, I don't know. Yeah, let's see if it's gone. It's gone. Okay, so we come back to P of m and n. All right. So we should clearly sum up all the, we should look at, we have an event in mind. The event is that after n steps, the person has reached a certain site m, wherever. Okay. Question, of course, that could have happened in many ways, right? You could have reached site M by taking, so many steps left, so many right, and then coming back, or doing this or doing that. So there are many ways of doing it. So I think it's fairly evident that we should add up the probabilities for each of those, and when you do that, the answer is simply NCM. Sorry, actually it's not. Let me backtrack. Okay. Location M. Let's do the following. Let's introduce the following idea that there are n sub r rightward steps that I took during the walk. Okay. And let NL be the number of leftward steps that I took. Okay. Then I think it's clear that NR plus NL equals N, right? It's also clear, I think, that NR minus NL equals M. Think about it for a minute. Because wherever you reach, whichever way you've gone, you've taken a number of rightward steps and a number of leftward steps. So the number of rightward steps minus the number of leftward steps will tell you where you are. Is this clear? So NR minus NL is M. Therefore, you can express M, if you like, in terms of NR and NL, but whatever. So you can parameterize M and N by NR and L, but the answer then clearly is NCNR divided by the total number of options, which is 2 to the n, which I'll just write as 1 over 2 to the n here. NR is a proxy for M for a given n. Is this clear? Okay, so then we are sort of we know the answer to the question we asked. This is the answer written down in fairly straightforward combinatorial way. Yes? NL minus NR will be minus M. Oh. Yes, that's the difference. Right. So NL minus NR will equal minus NR minus NL. No, I guess I'm not catching your question. Yes. What are you asking? Yes. Well, it also tells you something about the location, and it gives you the negative coordinate of the location, and by location we are using the usual convention that rightward is positive and leftward is negative. So that I have used. So this is the answer to, I think, your question. No. We are asking for the location. By location, I mean the coordinate. Negative locations are allowed. NR could be smaller than NL. Okay, so, okay, is that what is confusing? I'm not saying NR is bigger than NL, alright? So I'm starting here. I could land up here. I could have landed up there. If I landed up here, I would have had to take more my right steps than left steps, and vice versa. Is this all right? It's a coordinate. I mean, maybe location. No, location is okay. Location is position. It's all right, I think. But are you all okay? No modulus. Okay? Exactly. If NR is bigger than NL, then you will be on the right hand side. If the reverse on the left. And if NR equals NL, you will be back at the origin, which is a especially interesting case, as we will see later. Okay, so far so good. But now let's ask what happens if you do this many times. So if you do it many times, of course you have, okay, by the way, you all know, of course, that this is Do you think it's really the battery? So, Shamit, there's a humming sound all the time. It's coming. So, somebody said it's due to the low battery, but perhaps it is. Okay, so let's replace it as a new. Okay, fine. So, this is 1 over 2 to the n times n factorial divided by. Sorry?
No, I think it's maybe
Oh.
just the direction.
Yeah.
To become. So the red color is on, that is the red.
Oh, okay. I thought this was.
No, this is.
Okay, am I back? Okay. I'm really back. Change the mic. Okay. Yeah, I have all sorts of things. Change is rare, but I. Okay, something fell down, but it's all right. I'm ashamed to do this. Okay. Now I'm ready for security. Right. Okay. I've also changed. Yeah. Okay, so I think I'm okay now. Let's go. All right. All right, so here we are. I forgot to complete this. This is n minus nr factorial, which is the same as nl factorial, by the way. But okay, this is what we have. But we want to know what the answer is for large values of capital N. Okay. So you'll have heard perhaps of the Stirling approximation for the factorial, and we are going to use it. But before we do that, let's take a small aside and come back to this in a minute. Okay, and the aside is simply the following. Okay, so let me also write down nr is equal to n plus m over 2 and nl is n minus m over 2, just for reference. Okay, now, right, so, you know, if you like, we can write this in terms of n plus m and n minus m, but we won't do that right now. Okay. Argument I'm going to take you through right now is going to say that at large values of n, namely after many steps, m will be typically large, but not as large as n. Okay, so the argument is separate, and in fact this argument you will find in Feynman's volume 1, and it's a very simple and nice argument. It says that if you are at site m after n steps, so let's call this m sub n, then at the previous step, or shall I just, yeah, at the previous step you could have been either here or there, right? So therefore I can write an equation which is mn equal to m sub n minus 1 plus delta, where delta is plus or minus 1. I don't know which one. Depends on the actual sequence. But then I can square this. Right? This is true just by squaring something. Now let me take an average. The average is over all histories, which And so let me just do that by putting an average value here everywhere, because if something is true history by history, it will be true for the average. So this is true. I have a simplification right here. Delta squared is equal to 1 because delta was plus or minus 1. The other simplification is to notice that when I take a step, I don't care about where I am. Therefore, these are independent. So this will factorize into 2 times mn minus 1 times the average value of delta. 2 events are independent. The expectation value of the 2 will factorize in this way. I think this is fairly clear. But the average value of delta is 0 because it's plus or minus 1. So this term does not contribute at all. So this sum on substance of this is that mn squared is m sub n minus 1 squared plus 1. And you can iterate this starting from n equal to 0, where m was 0, up to n, and then you conclude that mn squared is actually equal to n. Therefore, if I take a square root, which I would in order to think of a typical displacement, of course it's an average and then you are taking a square root, so it's the root mean squared displacement that is proportional to root n. Now, why did I do this? It's because before we apply any approximation or anything to this, we should be clear on what we are doing. We are thinking of large values of n, but the typical value of m divided by n will be small. It will be of order 1 over root n, typically. So this guides what we will do here next. Okay, so let's go ahead. Why what?
Why root a square?
Okay, so just to quickly go through the argument again, this was clear and then this was algebra up to here. When we take an average, this drops out and we get this. Now, okay, so how do we go from here to there? We start by saying when n equals 0, no step, m was 0. M was 0 and m, so m squared, everything was 0. Right? Now you iterate. So what does this say? n equal to 1. So m1 squared according to this will be m0 squared plus 1. m2 squared will be 1 plus 1, 2. Therefore, mn squared average will be n. Okay, is that okay? It's just iterating. Now, so guided by this, we come in and do what we want to do. Okay, so we'll take a log of p, that's convenient to do. Okay, and I'm going to use the Stirling formula. Up to a certain order. So this Stirling formula is actually, Stirling has a series. It's an asymptotic series. Now, asymptotic series have certain very nice and peculiar properties, which I will not get into at this moment. Maybe in the tutorial we will, and we'll illustrate. But since we've started on the point of asymptotic series, if you have a system which you want to represent by an asymptotic series, some function, don't keep too many terms. Advice, because you will go crazily out. Don't keep too few also. If you want a good approximation, keep an optimal number. But this is not relevant to what I'm saying here, but typically if you have an asymptotic series and you're asking for the order of the series, you have a series and you've kept n terms in the series, here's the actual answer. As you keep increasing the number n, you'll converge very, very well to the answer, and then suddenly you'll begin to depart and depart crazily. So this is easy to show. It comes from the fact that asymptotic series have an essential singularity. There's no radius of convergence 0, but keep it in mind. Stirling is asymptotic. We'll keep a few terms. Okay, today. All right. People are looking puzzled. Yeah, first time I encountered this crazy property of asymptotic series, I was, in shock. It's, I don't know, some of you look puzzled, some of you don't, but what I've said is true. So be careful, it's a caution. Okay, but we approach things cautiously. So we are okay. All right, now I have the wrong page of my notes. Let me just carry on here. Log P. So Stirling, I'm going to use it up to a certain order, and what I'll do is log n factorial. Yeah, where am I? Often you use Stirling in the form n log n minus n, which is okay. I've gone a little further than that and kept a few more terms. All I'm going to do is use this substitute here and work out. And if you will forgive me, I may not do all the algebraic steps. They're simple, but important that you do them. Okay. So let me just should I write down maybe the first line of this? N plus half log n plus half log 2 pi minus n log 2. Where did this come from? This came from 1 over 2 to the end. This is that. This is the numerator. Likewise, you have terms in the denominator, and I won't write them all, but well, okay, so similar terms. Should I write them? I'm in two minds. N over 2 times 1 plus m over n. Let me write one term. Plus half log n over 2 1 plus m over n minus n over plus one more term with m going to minus m. Okay. This form has come in simply because by using this, pulling out an n and so on and so forth. So there's sort of trivial manipulations to be done to get this, and then you keep on and on. Okay. Remember what we said on this side of the board? We said m over n is small, and we will use the smallness of m over n, and we'll expand this. Is this all right? So it's sort of simple steps, but you have to work them out. So I won't do the algebra. There's some 3 lines in between. I mean, if you want to. So this turns out to be equal to minus half log 2 pi. Collect terms, expand, nice cancellations always, and you'll find that this is minus half log 2 pi minus half log n plus log 2 minus 1 half. So what we're doing is we're expanding to quadratic order in m over n. M over n is small. So we have one last term, which is the quadratic term. Let me write it as half times m squared over n times 2. Okay, I mean, you can cancel some of the 2's if you like. I mean, it's sort of natural to write it this way because there are 2 terms, m and m minus n. There's a half from the Taylor expansion, there's another half that comes in. So this is what it is. Well, so this is very nice, but remember what this was. This was log p. So p turns out to be exponentiated. squared over n. Okay, take it from me, this is correct. Including this strange factor of 2, which you may not have expected. Okay, we'll see in a minute that it should be there by taking a continuum limit. So are you all with me so far? We've done something very simple. We've taken a what's the word? Combinatorics, and we have applied Stirling and we've gotten this answer. We've used m over n is small, but that's justified. Go to the continuum limit in the following way. Let's say the lattice spacing here between any two successive points was A. So now I'm going to a physical space where I have not points on a line, but actual centimeters and stuff. Okay, so let's say the lattice spacing was A, but I'll take the limit of A being very, very small. So A is very small. So that on my description, where I have a certain point x and a certain increment x plus delta x, there will be many, many, many A's here. These are all the points here. Okay? Now comes this factor 2. It's interesting. So suppose you wanted to write now, I'm using the same symbol, forgive me, P of x for the probability density. What will P of x mean? P of x multiplied by delta x will give me the probability that I'll end up in this region. I've started at the origin, which was somewhere here. I've reached x, and I'm in between x and x plus dx. Okay. Now, how do I make contact with the description that I had? Well, so that will equal P of mn, where n corresponds to being here. How many points are there in this? But I'm told microphone is required for YouTube. Not that I'm a big fan of YouTube, but YouTube, forgive me. What should I do? No, yeah, change it if you like. I mean, I have no objection. But in the meantime, what will you divide by here? We want the number of points. See, that's what you and I would say, but it's not so. It's 2a. This is the 2. It will cancel that 2. Why did it come? Think about a walk. If I take 4 steps, where can I be? If I can be at 0, I can't be at 1. I can be at 2, I can't be at 3. With an even number of steps, I can reach only an even value of capital M. With an odd number of steps, I can reach only an odd value. Therefore, given a large, about 1,000 of these here, only about 500 will be accessible for any value of n, because n is either even or odd, can't be both. Therefore, the number of successes that we are counting are spaced 2a apart for that value of n. So this is why we introduced this fact. Okay. Chandrasekhar has, of course, not described it in such gaudy detail, but he's correctly pointed this out, of course. Right. Now, so of course, we plug in and we find P of x. So that's 1 over 2a times Pmn is okay, fine. 1 over root 2 pi is 2 pi a squared n e raised to minus half x squared divided by n a squared. This is the result. So, what have we done? We have gone to, in some sense, a continuum space description, but so far time is discrete, because there is a step every, somebody has a metronome and they are doing that. So, you take a step, but actually, there is absolute space, there is absolute time also, yes? That is the most probable, yes. No, because n is increasing all the time. But one stationary means that things don't change. It is changing. It is changing all the time. But we are looking at changes when n is large. But n is large, but it can be larger. So things will change even more. We are coming to it. Slowly we are coming to the physical description. Okay. Yeah, n tends to infinity. N is not infinite. N is large. Okay, we will come. Right. So we actually have these metronomic beats. This was a good place to do it. Somehow it was resonated. Yeah. Okay. All right. Tap. Suppose we have r beats per second. So the frequency is r. Let r equal the rate of steps. Then in time t, okay, n of course is RT, so t is equal to n over r. N in time t, there are r steps per second, so in t seconds there are n steps, and this is the relation written in some way. So n is equal to RT. So then we can write, see what's coming in here is NA squared 2 dt, where d is half r. I am just writing it this way. Check that if you do this, then this is true, provided d is written this way. So d is a very important and fundamental object. It's called the diffusion constant. Okay. It's given in terms of your microscopic model of the Walker through this relation. Dimensionally, centimeter squared. Oh, nowadays it's meters. Sorry, we grew up in the time of centimeters, if not inches, right? Anyway, centimeter squared. R has dimensions what? It's the number of steps per unit time, so it's a rate. It's 1 over time. So this is centimeter squared per second. That is the unit of the diffusion constant. Okay. Now having done that, of course, I can rewrite this P. This was P, x and n. But I am going to now rewrite P as a function of x and t, therefore, as 1 over root 4 pi dt, form instead of 2 because of this extra half in the definition, 1 over root 4 pi dt, e raised to minus x squared over 4 dt. So this is a the way people usually quote the answer for a diffusion process. There is such a thing as a diffusion constant. It depends, let's say, if you're talking again of a colloidal particle diffusing in water, for instance, it will depend on the particle, it will depend on the mass, the size, etc., of the particle. It will depend on the temperature, it will depend on many things. But given a particle, given the surroundings, given the rest of it, it's a constant. It's a constant, it's called diffusion constant because it's constant during this process. Like other constants, like spring constants or other constants, it can depend on other things like temperature, pressure, etc. That's another point. Okay. That's correct. So, the proper limit to take is of course a going to 0 to get the continuum space limit, and equally if we want to take the proper continuum limit for time, we should take the limit r going to infinity. So, this is strictly speaking valid if a goes to 0, r goes to infinity in such a way that r a squared is a constant. Okay. So, this is, so if you read Feller, you will have to sort of flip through the chapters to find the relevant section. He will describe this limit quite nicely, such that r a squared equals constant. Okay, now having worked through this and gotten this answer, let us at least get some feeling for the answer. So, how do you get feeling for anything? Plot graphs. Nowadays I find people are losing the ability to plot graphs. I mean, teachers, you all must have noticed, your students I won't address you all. Okay, but let us see, how do we plot a graph? Well, we plot this function, that is what we want to do, except we want to do it at different times. What happens at time 0? Time 0 particle is sure to be at the origin. Okay, so it is a big fat delta function, I won't draw it. So, at a very small time what happens? Well, x squared of order dt. So, this will be substantial provided x squared is of order dt. It will be, when x becomes bigger than that, it just goes to 0, crashing. It is a Gaussian function. So, it looks like this. Okay, not that my plots are very good, but right. Okay, that is my representation of a Gaussian. Let some time pass. So, it will get bigger, but it will fall down. Why will it fall? Because the integral below this curve has to be 1, right. Integral dx pxt is always 1, because the particle will be somewhere. Okay. And if more time passes, it will fall further. So, this is the sequence of events. So, your question, is it going to be found near the origin? The most probable value is indeed near the origin, but the value of being at the origin falls in time. In fact, you can read it off. So, the probability to be at the origin at time t falls as 1 over the square root of time, but it is still the most probable. Okay. At this point, let me read out something. I should have, I hope it's, this battery has not gone. So, the first person to introduce the word random walk into into physics, or for that matter into English, was a biometricist. His name was Carl Pearson, very well known person in those times, and this is the year 1905. It is the year famous for other reasons, which students of physics will recall, but he wrote. Okay, so let me just. So, in those days, the people wrote to journals not only because they had results, but because they had questions. So, he writes to this journal you may have heard of, Nature. Nature, it is a well known journal, and Nature, July 27, 1905. So, Carl Pearson writes, can any of your readers refer me to a work wherein I can find a solution of the following problem? A man starts from a point O, that is his problem, walks L yards in a straight line, yards, not meters. Okay. So, L, like that. Okay. And turns through any angle, walks L more yards, turns through another angle, walks L more yards, then keeps doing this. So, you can see some sort of random walk, it's a generalization of the random walk on a plane that is going on. He repeats this process n times. I require, he wants for his work, the probability that after these n stretches he is at a distance between r and r plus dr from his starting point O. So, as you see, we have sort of begun to answer his question in one dimension. Very simple to generalize exactly what you have done to two dimensions. So, it is not a big deal. But the interesting thing is that within 15 days he writes to Nature again. You might think he will ask another question. No. Readers from all over, I don't know where, have sent him letters with the answer. So, he says, I have to thank several correspondents for assistance in this matter. Now, see what he says. I ought to have known it, but my reading of late years has drifted into other channels, and one does not expect to find the first stage in a biometric problem provided in a memoir on sound. Then he goes on, let me finish, then I will come back. The lesson of Lord Raleigh's solution is that in open country, the most probable place to find a drunken man who is at all capable of keeping on his feet is somewhere near the starting point. Okay. All right. No, so we've also seen it. This is the most probable and so on. But what is most interesting is this, I ought to have known it, but see, he's apologetic about not keeping up with developments in acoustics. But see, that is the way you should be. You should keep up with everything. I mean, not only your teeny tiny field, one should keep up with what is happening in physics, and this is part of the aim here is to at least alert you to the historical, sequence of events, and So, by the way, it also points out to the wide applicability of random walk theory, or the problems we encounter in random walk. They occur in acoustics, they occur here, they occur there, they occur everywhere. Okay, but this was Carl Pearson, right. So, here in some sense in one dimension is the answer to his question. In any dimension the answer is 1 over t to the d by 2, simply because this Gaussian generalizes coordinate by coordinate x, y, z in a sense, and then the normalization has to pick up this t to the d by 2 in any dimension, but we will not enter into that right now. Now, so far we have talked about typical excursions and typical things that happen, but it is also possible, although very rare, that I might take all my n steps in one direction, and I might land up quite a distance away, which is proportional to n rather than root n. What happens then? So, what happens then is the subject of an exercise that you all will have to do. So, I just bring to your attention the exercise sheet. There are n copies of the sheet here. Please, after the lecture, pick up one. Think about these. We will discuss them in the tutorial on Wednesday. Is that okay with you? You want me to do it tomorrow? Yeah. No, you remember the. Yeah. Okay. All right. So, on Wednesday, so please attempt these questions, and I will tell you the rough way the answer goes. Basically, up to the factorial point, there is nothing to be done. It is the same, but do not make the small m approximation that we have made here in order to do this. Okay. So, show that okay, you will find it here, but the probability of having very large m, m of order n, is p of mn. Show this, this is part of your sheet, falls exponentially in n, multiplied by a function which depends only on the ratio of m over n. So, the statement is that after large number of steps, the profile will look something like this. It will resemble a Gaussian very closely up to a certain point, and this also we will illustrate, on in the tutorial. But far away, near the tail, this drops exponentially, and this is the subject of your exercise. Is the statement clear? Maybe the proof is not, but you can find the function phi. You will find it has a very familiar form once you tackle it. Okay, so Gaussian is right, but it's not right towards the tails. That's all I wanted to say. Okay, good. You don't need this. Now, see, what we've addressed is a very simple and well stated problem. The walker just walks right or left with equal probability, and you can generalize this immediately in many ways. For instance, who says the walker has to move? Maybe the walker won't move, it'll just stay there. You can ascribe a certain probability to that, etc., etc. Certain probability of not moving, and if it moves, then equal probability right or left. That is one generalization you can make. You can think about that's, by the way, also one of your exercises. And second question, maybe you have unequal probabilities to move right and left. What would happen then? Maybe you don't always keep the same step length. Right now you might do this, next time you might do that. Can you answer? Turns out, in almost all cases, the answer is a Gaussian. Okay, and we will show this now in some other way. So we are taking up what Chandrasekhar in his article calls random flights. So we imagine we are birds, we can fly. So this is not a random walker, it's a random flight. So just to have a setting, let us consider continuous space from the start. So my step length could be anything. Of course, not totally anything, I'll constrain it a little bit. But time will be still in steps, discrete time. Okay? So we have a motion not unlike what we had earlier. Okay, let's say we confine it right now to one dimension, let's say. So we have a hop like that, maybe a hop like that, maybe a third hop like that, etc., etc. Okay, and we are asking about this motion. Is the physical context clear? The rule will be that there is a certain probability distribution which I prescribed from the beginning, from which I will draw the step length. Is this clear? Let me repeat it. So I have a certain probability distribution of taking a step length x, which I am prescribing at the beginning. Okay, for instance, the distribution may look like this. I mean, I don't know, something which is something or the other. This is prescribed, and I'm asking what is the effect of this after many, many steps. Answer is going to be a Gaussian, let me just tell you. Somehow Gaussians just pull in everything. This is part of what in mathematics is called the central limit theorem. Have you all heard of central limit theorem, most of you? Yes. Okay, so let's go through this. At some point I'll actually tell you the statement of the central limit theorem, but not right now. Okay, so we are saying there's a probability distribution P of x for the step lengths, each step. Then clearly if I take a step of length x1 in my first instant, a step of length x2 in the first instant. When I say length, I don't mean length, I mean displacement. It could be positive or negative. Okay. and so on. Then after n steps, I will have reached a point which I will call capital X. Is this okay? That after n steps, if you like, I'll put a subscript. Let me not. If you want, I'll put it on this. But x sub n after n steps. It's the sum of these displacements, right? Now, now pay attention to the next step, because this is an important way of solving many problems in probability. So, just think about this. I want the probability, in fact, that I am at a certain value of x between x and x plus dx after n steps. How could I have done it? I could have taken one enormous step first and then some few steps around that, or I could have done a sequence of the many ways in which I could have gotten. At the outset, it seems almost impossible. How are we going to do this? We'll show it can be done in 3 lines. So pay attention to the 3 lines. So p of x is actually, this is a multiple integral dx1 through dxn. Okay. So let me, okay, sorry, let me change notation a little bit. Let me not call this double, this is single p. Okay. All right, and let me backtrack for a minute before I write this expression. So remember, I took one step here to n steps, and I chose this. What is the probability that I will associate with this sequence? Well, it's going to be p of x1. Next step is independent of what happened earlier, times p of x2 through p of xn. This is the probability of this event, okay, between x1 and x1 plus dx1, etc., etc. Okay. So this I could, if you like, call p of the corresponding capital X. The probability, well, yeah, no, perhaps I don't, but no, this may be confusing. We will just remember this is the probability of having these guys, right? Right. So what am I doing? Here, of course, we knew that x1 plus x2 plus up to xn actually added up to the x that I have. So this was okay. Now I'm asking a different question. So given all these, I got an x. But now I'm insisting on a certain x, capital X. Capital X is what I want. x1s and x2s can do anything, but they better add up to x. So how will I do it? The probability of this to happen is px1, px2, pxn. And if I had only this, that won't work, because if I integrate over dx1, px1, I'll get 1, 1, 1. This is not telling me anything. But I have to insist that I'm at capital X. So how do I insist? I put a delta function. So let's do that. Delta of capital X minus summation xi. So understand this step well. So it says integrate over all possibilities x1, x2 through xn. Let x1 be anything, x2 be, but count only the ones which give you capital X. Is this okay? So this delta function plays a crucial role. It counts only the ones you want. So this is important to understand. And this is a good strategy. I mean, if you have an event that you want, an event is that you'll end up at capital X, look at the ways in which you can reach it and just insist that it is there by putting what is called an indicator function. It indicates whether the event is there or not. Event is there if the delta function is satisfied, and not if not. In a discrete setting, you would have a Kronecker delta, but here let's have a delta function. So far so good? Any question on this? Yes.
Why is it x minus some x instead of delta x minus x
Okay. All right. I mean, yeah. So there is some leeway in each of these x's, but that corresponds to a leeway in x to x plus dx. You know. So when we have p of capital X, what does it mean? It means that p of x dx is a probability, not p of x alone. P of x is a probability density. So there is a leeway in, you know, of size dx in asking for the probability that I have, you know, something between x and x plus dx. So this is you know, a partial answer to your question. Your question was why don't I have dx1, dx2, etc. hanging around? I don't, because I'm dealing with probability densities themselves. And if I want something precise, okay, the chance of getting something precise is going to be 0 unless I have a multiplication dx. But at this stage, I'm asking for something precise, namely I. No, it's not an approximation. It's exact in the continuum limit, because each of these are probability densities. Okay, so I'll just leave it at that. If you like, you should repeat this argument on a discrete, with a discrete, you know, in a discrete setting, and you will see that integrals are replaced by summations. This is replaced by Kronecker delta, and we are taking the limit of that process, if you like, to make a delta function. These are probability densities. So probability density means, you know, it's the that multiplied by dx gives you a probability of being between x and x plus dx. Okay, so maybe we will discuss this later in the tutorial or wherever. Any other question? Okay, so I'm going to proceed. So now how do we tackle this? Well, so what we do is very simple. We write down an integral representation of the delta function. So you recall the delta of y is 1 over 2 pi integral from minus infinity to infinity e to the I q y dy, or dq, sorry, some variable q, right. So I'm just going to plug in and see what I get. Well, so then what I'll get is simply 1 over 2 pi integral dq, okay, product over dxk. Okay, sorry. So I need to insert this, right? E to the I q x minus summation xi, right? I have an extra integral over dq. I still have my x integrals to do. I'll just write those as product I equal to 1 to n, right? dxi pxi, and let me do something. Since I'm on a blackboard, I can do it. I'll just knock this out and put it in. So e to the minus I q xi. E to the I q summation xi, I am breaking up into many e to the I q x1, x2, x3 up to xi, and therefore landing up with this. Okay, but you see, each of these integrals is the same. Integral over dx1, dx2, etc. It's the same integral again and again and again, n times. This product over the integrals is an integral of pxi e to the minus eq dot xi. So let me call any one of them. So let me put the integral here, and let me call any one of them p hat of q. Okay, I can define a function p hat of, it's the Fourier transform of the probability function px. Okay, and let's call it. By the way, what is p hat of 0? 1. That's right, because q is 0, you have an integral over pxi, and that's 1 by normalization. So it's a nice regular function. It's nothing very bad about it. It's, you know, okay. P hat of q, good. So see the advantage of what we've done. What we have is, of course, quite a neat form. It's 1 over 2 pi integral dq e to the I q times capital X times p hat of q raised to the nth power. Okay, now within 5 minutes we will get a Gaussian out of this. Yeah. Okay, so here goes this board. Okay, so what am I going to do? Okay, I am going to assume, okay, let me, so we will expand around q equal to 0 for a good reason. We will tell you in a minute why. But suppose you expand around q equal to 0, then p hat of q is 1 minus I times q times the integral x px dx, and then the next term is q squared by 2 minus half q squared integral x squared p of x dx, etc. Okay, let me assume for simplicity, although here I have worked out the more general case, but let's assume that, suppose, notice that this is the average value. This is the average value of x for over all the step lengths. This is the mean squared, etc. Let me assume that the average value is 0. Okay, it will just simplify writing. It's as easy to keep it, but let me consciously not do it. P of x then. Okay, so wait on. So before p of x, let's write down p hat of q raised to the nth power. That is what we need. So that's equal to 1 minus half q squared average x squared to the power n, which to the order that I am interested in of q is the same as e to the minus half q squared times n, times of course average value of x squared. Because if you expand this out, this is the first term. This is the form we will use here. So now you see where your Gaussian is going to come from. So capital P of x, capital P of capital X is equal to 1 over 2 pi integral dq e to the I cube capital X e to the minus half q squared x squared n. Right? Now you recall something from analysis, Fourier analysis. The Fourier transform of a Gaussian is a Gaussian. Everybody knows that. Right? So this is equal to, well, so here's your Gaussian finally, e to the minus 1 half capital X squared. This was in the numerator of the exponential, it will be in the denominator here, x squared times n is also here. And of course, there is a normalization, I mean something on completing that Fourier transform. So, that is 1 over 2 pi came along, and then you have root 2 pi over n sigma squared. Oh, sigma, sorry, I used the notation sigma squared for x squared, but since I haven't introduced it, let me not. Is this okay? Let me complete this and then just point out a few things. This is it. This is the answer we wanted. But this is quite a general answer. I mean, you could have taken steps of any length. So it should include this first thing that we started with, that the step had to be of length a, either right or left. So this should be included in this. Let us do it as a check. So we do a check. Check. So if I insist that my step length is either a or only minus a, the first thing that I started with, then my little p of x is a delta function with length a, or displacement a or displacement minus a, each with probability half. So this is what it is. Then I recover my first thing, and then you can easily evaluate average x squared is therefore a squared, evidently. So p of x, then in that case, special case, this one is what is it? E to the wherever e to the minus half x squared over n a squared over root 2 pi which we had written as e to the minus x squared over 4 dt divided by root 4. So we actually recover the answer as we must. But now we've gotten a whole lot of infinite number of other cases already solved, because p of x could be anything, almost anything. Now we will qualify it. All we have assumed really is that average of x squared is finite. Now, is average of x squared always finite? Yes.
Initially, you have not assumed any single form of small p.
That's correct.
But it turns out that p of q is Gaussian. So
Yes.
But is there any does that mean that your copying probability is also Gaussian?
No, they were not Gaussian. They're not Gaussian. The p of x could be anything.
But you said that the Fourier transform of Gaussian is a Gaussian.
Yes, Fourier, that is a mathematical fact. Yes.
It will be of q, that's a Gaussian.
Yes.
And small p of x is nothing but the Fourier transform of
Okay. No. So let us be clear. Little px is not Gaussian. It is emphatically not Gaussian. So on Wednesday, with your help, we will try to show you what happens if you take very different functions for p of x. It could be, for instance, p of x could look like this, or it could look like this. This was our initial case. Or it could look like that. Or it could look like even this, but falling little fast. Okay, it could be a Gaussian. If it were Gaussian, no problem, but certainly not assumed to be a Gaussian. No matter what the distribution, the sum of the variables is distributed as a Gaussian. This is an amazing fact, and it converges to a Gaussian quite quickly. I mean, by the time you add 2 or 3, depending on your starting distribution, you will see a Gaussian form emerging. By the time you go to 10, it's pretty good. I mean, you can't distinguish from Gaussian. So the limiting form is a Gaussian. It is in principle only in the limit very, very large end, but in practice it actually holds very quickly, very well. Although this thing you started with is far from Gaussian. So it's an amazing fact, it's a fact. And this is the sum and substance of the central limit theorem. But all theorems have certain assumptions. And the assumption which I have not told you about and which we have used is that x squared is finite. We have assumed. In other words, the variance is finite. Variance, right? That's what I want. Variance. Okay. Are there distributions in which the variance is not finite? Yeah, there are many of those also. And they're becoming increasingly important in current day contexts. But of course, there's an equally large number of distributions or larger in which x squared is finite. And for all of these, the answer is a Gaussian. So this is illustrating the central limit theorem. The central limit theorem is a strong statement on how the sums of random variables are distributed. It's not put in the setting of random walks, but we can use the setting of random walks to talk about it. What are the random variables? They're the step lengths. What is the sum of the random variables? It's the displacement. It's a very physical thing that we are asking. And the answer is a Gaussian always. It's amazing. Provided x squared is finite. Now you could ask, yes. No, we have not said that. No. Okay. So we have used a key, at a key point, we have used the fact that average x squared is finite. It is at this point. Okay. All right. First of all, why did I stop my expansion at low order in Q? The answer is that I am going to be interested in large values of capital N. And it suffices, not that I have to stop, but it suffices to stop at a small q. Okay. What is multiplying q squared is in fact average x squared. I am assuming it has a value, it is not infinite. If it is not infinite, you can call it sigma squared, and then you will be more assured it's a number, sigma squared. Okay, so why is this true? Here I am using slightly iffy thing on smallness of q. Okay, so this I am not doing sort of mathematically rigorously, but what you need to do is to evaluate really the asymptotic value of this integral. That's what you have to do for large n, and there is a well laid out procedure. You will find it in mathematics textbooks. Like I would recommend look at the book by Bender and Ortzag, which is a very practical book on how to do asymptotic expansions and so on. And what you do essentially is what I've done. Okay, so I'm not giving you the mathematical niceties of how to evaluate these integrals, but that's the essential point. Okay, so this with this is that. You could ask, what is the situation if x squared is not finite? Are there such distributions? There are many. We will just write down one of them. So for instance, if you have a distribution p of x, suppose is 1 over 1 plus x proportional, you can normalize later to the 1 plus some alpha, where alpha is between let's say some value of alpha which is not which is maybe less than 1, let's say alpha equal to half. How does this fall at large values of x? It falls as 1 over x to the 3 by 2 in the case I've chosen. Okay, so when you have a distribution that falls that slowly, by the way, it's not so slow that you can't normalize it. Integral of 1 over x to the 3 by 2 is 1 over x to the half, which is well behaved at large x. So, this is a normalizable distribution, but clearly average x squared, which will be the integral of x squared dx. So, average x squared would be integral x squared over x to the 3 by 2 roughly dx. This will diverge. Okay, so you might ask, okay, fine. Suppose my step lengths are this large, like that. How will I tackle this? Can I tackle this? Yeah, answer is yes, you can tackle it, don't worry. Answer is not going to be a Gaussian, but it's another function. In the case that I've written down 3 by 2, it's a well-known function in the astronomy context. It's called the Holtzmark distribution. But in general, for other values of alpha, it is one of the very important class of distributions called the Levy stable distributions. Okay, so you should be aware of this. Accent put correctly? Okay, right. Okay, sorry. Okay, Levy stable. So they come into the picture, and you can ask, okay, but are there actual processes in which you have Levy stable distributions? Answer is yes. You encounter them every night, actually. I mean, well, not in your guest house, but in, let's say, in Bombay or some in Colaba. Okay, perhaps other parts of Kolkata. You have mosquitoes. Mosquitoes do random flights. Have you seen a mosquito flying? What does it do? Then there, before you can get. So the large probability of making large steps. If you integrate over a mosquito flight and take the second moment, you'll find it's infinite. I haven't done it, but try. So these things occur all the time in nature and physics everywhere. These distributions, but don't get carried away by them. Still, the most important and the most sort of robust of them is the Gaussian. That's the point. Okay, so right now, okay, I think there's no point starting to discuss the next thing I wanted to do, still sticking with the random walks at the moment, is to discuss a biased random walk where the particle is more likely to move right than left. So I'll just tell you the problem we'll take up next time, and that is the problem where the walker is more likely, let's say with probability p, to move rightward than leftward. So p plus q will take to be 1, and we'll just work everything out. And what do you think will happen? Will the walker move bodily in one direction as opposed to the other? Yes, it will. So what will happen physically is that the walker will acquire what is called a drift velocity. It will move, it will drift. It's not that it's every step it's moving, but it's moving this way, but over a long time. What's the definition of velocity? Distance divided by speed. So after a long time, it will move in one direction. And clearly the motion amount it moves will be proportional to the time. That's what we mean by speed. Distance divided by time is finite. So then, but the diffusion is leading to broadening that we saw. Actually, I didn't emphasize that, but let me do it again here. This broadened amount is proportional to the square root of time. Right? It's broadening in proportional to square. So if you have something moving proportional to time and broadening proportional to square root of time, it will move more than it broadens if t is large. Okay? So it will describe something like a Gaussian, which is broadening as it moves, and then it moves along. So you might think that it turns out there's an interesting interplay of the speed and the diffusion constant, and there's a certain time you have to cross before this becomes apparent, and before that diffusion dominates. After that, drift dominates. So we'll come to a discussion of this tomorrow. Okay, lecture is formally over because it's 1 o'clock, but questions are, yeah. No, can you repeat? No, 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 no. No, it is not every time. I actually did it for no very good reason. I mean, if it's not 0, what you have to do is to put in here x minus mu n. This is the answer in general, where mu is equal to the average value of x. So, this is analysis is very easy to generalize and get this answer next time, and we will actually see it with our biased random walk. Yes. If no, it's still a Gaussian. It's still a Gaussian, but okay, let me just describe the sequence. But it's a moving Gaussian. So, if average x is not 0, okay, let's say it's positive, then to start with it's very close by. To end with, what happens is that this broadens a little bit, but the what's it called, the top value, mode, most probable value. Most probable value moves right. Okay, it doesn't. After a while, it has moved quite far right, so it will be. But the shape is always Gaussian. Then it moves here. It has broadened more, but it has moved much more than it has broadened. But you know, in the beginning, it's quite interesting. There's something called the diffusion time. It takes a little time before the speed dominates over the diffusion constant. Okay, yeah. I did.
So the central limit theorem, that holds also for if the probability distribution is same for all the values x side. So if the probability is dependent on the side, then it should not be Gaussian.
Well, so it depends on how it depends on the side. See, so what you have to do is you have to have a probability of having a certain probability distribution, right? I mean, that's what you need to do. You have to parameterize the probability distribution and say that there's a certain probability, that this is the probability distribution, that is the probability. Turns out that for a large class of it, once you do and the dust settles, you still get a Gaussian. Okay. So, basically, this average x squared in that case is replaced by average of average x squared. Sorry. So, this is, how do I do it? Okay, average x squared, which is for a given distribution, your probability distribution. Let's parameterize your probability distribution by lambda. As you change lambda, your distribution is changing. For a given lambda, you have a given value of x squared. Okay. Now, suppose, so by the way, you have a parameterization with lambda, so there should be a probability of having a certain lambda. Okay, what is lambda? Lambda might say that, you know, my distribution could be this, or it could be that, or it could be that. It will parameterize your. So, there is a certain probability of having lambda. So, let us say you have a probability p of lambda for parameterizing your distribution, probability distribution through lambda. If this is finite, Gaussian. Gaussian is sort of super universal. It's not infinitely super universal, because it does fail once the variance becomes too large, but it's remarkably super universal. I mean, I don't like to use these words, but okay. Yeah. Okay, so Gaussian. Okay. Can we stop? Okay. Okay, thank you. Sorry? No. As Professor Mukunda said very well, save it for the last. Don't forget, n is there, but it's finite. So, it's large but finite. It's actually 60. Shall I distribute this or will you all come? Huh? Okay. Oh, good. So there might be, I haven't judged, but you might need 4 or 5 more in the end. Yes. Right. Yeah, because
Then red and green and blue would do, no? Oh, अच्छा.